Hello everyone, welcome to our channel. Imagine you're building a small application, maybe a to-do list or a simple game. You have spent hours coding, but something isn't quite right. You keep running into errors, your program isn't working as expected, and you are frustrated. Don't worry, we have compiled some of the common issues each coder faces, and in today's video, we will cover the top 12 of these common mistakes so that you have a better understanding of how to avoid them. We will walk through each mistake with examples and simple demos so you can improve your coding skills. Let's get started. Our first mistake is the infamous off by one error. This happens when loops iterate one time too many or too few. Let's take an example to understand this better. Imagine you're meticulously counting from 1 to 10 within a loop, aiming to reach that perfect number 10. You start your loop with excitement, but something goes wrong. Instead of reaching 10, you find yourself halted at 9. Puzzled and scratching your head? This phenomenon is the off by one error, a tiny discrepancy with significant consequences. Let's take another scenario. Imagine you're baking cookies and the recipe says to bake them for 10 minutes. You set your timer, but it accidentally stops at 9 minutes instead of 10. The cookies come out undercooked. Just 1 minute short, but it makes all the difference. This is what happens when an off by one error in coding. In the world of coding, this error occurs when loops iterate one time too many or too few. But fear not, for there is a simple fix. By keeping a keen eye on your loop conditions and making a subtle adjustments, you can correct this oversight. For instance, changing the loop conditions from I less than 10 to I less than equal to 10 ensures that your loop includes 10, counting to the desired number without skipping the beat. Let's take up a programming example. In the code, the loop shuts down prematurely due to the condition I less than 10. This means that the loop runs as long as I is less than 10. Which causes it to stop when I reaches 9. As a result, the number 10 is never included in the output. This seemingly minor oversight can lead to significant issues, especially in the context where precision iterations is critical. In contrast, the correct code makes a minor yet impactful tweak to the loop condition. Changing it to I less than equal to 10, this adjustment ensures that the loop continues to run as long as I is less than 10 or equal to 10. Consequently, the loop embraces the number 10, granting us a complete count from 1 to 10. This fix might seem small, but it ensures the loop's behavior aligns perfectly with the intended outcome. Off by one errors, while small, can lead to significant consequences. They can cause programs to behave unexpectedly, leading to incomplete data processing, missing elements in sequences, and incorrect calculations. In critical systems such as financial applications or health monitoring systems, these errors can result in inaccurate reports or missing data, leading to potential financial loss or health risks. Be careful setting loop boundaries and understanding the behavior of your loops. You can avoid off by one errors and ensure that your code performs as intended, providing accurate and reliable results. Next up, we have the dreaded infinite loops. This occurs when the terminating condition of a loop is never met. Let's pick a scenario to understand this better. Imagine you are a baker preparing donuts for a big event. You set up a conveyor belt that moves the donuts through various stages for preparation. You need to produce exactly 5 batches of donut, but you forget to set the mechanism to stop after the 5th batch. The conveyor keeps running, producing donuts endlessly, wasting resources and causing a mess in the kitchen. This is exactly what happens when infinite loops in coding. They keep running without ever stopping, consuming resources and causing havoc. Let's take up an example. In the incorrect code, the loop lacks an increment statement inside the while loop, causing it to run indefinitely. The loop conditions I less than 5 is always true because I never changes, leading to an infinite loop. This is like the conveyor belt in our bakery store that never stops because there is no mechanism to halt it. In the correct code, adding I++ inside the loop ensures that I is incremented by 1 on each iterations. This makes the loop condition I less than 5 eventually false when I reaches 5, allowing the loop to terminate properly. This is like setting the conveyor belt to stop after producing 5 batches of donuts, ensuring efficient use of resources and preventing a mess. Infinite loops can do serious damage. They hog all the CPU power, making your system unresponsive and slow. This often leads to crashes that require a manual reboot. If you're processing data, an infinite loop can corrupt or lose data, and in financial apps, it could mess up transactions, leading to major financial errors. Plus, they make applications freeze or behave oddly, frustrating users and eroding their trust. Keep an eye on your loop conditions and make sure your programs know when to stop. Next, let's dwell into the world of data types. Using the wrong data type can lead to unexpected behavior or errors. Let me share a story to illustrate this. Imagine you are at a cafe and you order a coffee that costs $5. You hand over a $10 bill expecting $5 in change. But instead, the cashier hands you back a piece of paper with $10 written on it. Confused? That's exactly what happens when the mix-up data types in programming. Let's take a look with an example. In the incorrect code, age is defined as a string. So when you add 5 to it, it acts as a string concatenation rather than a mathematical addition. This results in 255, much like getting $10 as change instead of $5. However, in the correct code, age is an integer. So age plus 5 correctly results in 30, giving you the accurate change. Using the wrong data type can cause logical errors and unexpected results. Imagine working on a financial application and accidentally treating monetary values as text. This can lead to major miscalculations with totals that don't add up correctly. Similarly, in data processing, if numerical data is mistakenly treated as strings, you will end up concatenating values instead of summing them. This means combining numbers like 20 and 30 would give 2030 instead of 50. These types of mistakes not only make debugging harder, but also cause serious inaccuracies in your application's functionality. Always ensure you are using the correct data type to avoid these issues. Let's dive into the often overlooked but critical aspects of case sensitivity in programming language. This seemingly small detail can lead to significant errors if ignored. Imagine you are an event organizer at a massive conference. You have 2 speakers with similar names. One is Alice Johnson and the other is Alice Johnson with Alice being in capital letters. You accidentally mix up their name tags because you didn't pay attention in the case difference. As a result, they end up in each other's sessions, causing confusion and frustration for both the speakers and the attendees. This is precisely what happens when you ignore case sensitivity. It leads to mix-up and errors that can disrupt the flow of your applications. Let's look at an example. In the incorrect code, we declare a variable name with an uppercase n. But when we try to log it using name with a lowercase n, there throws a reference error. This is because of case sensitivity. And it treats name and name, that is with the capital letter N, as two distinct variables. In the correct code, we use the same case consistently, declaring and referencing the variables as name with the lowercase n. This ensures that the programming languages recognizes the variables and the code without any issues. Ignoring case sensitivity can lead to a host of problems that disrupts the flow and functionality of your applications. Firstly, it causes reference errors when the program fails to find a variable due to a mismatch in the case, halting execution and making debugging a challenge. These errors can be particularly frustrating to trace, especially in large code bases where variable names are used extensively. Ignoring case sensitivity results in inconsistent code, which is harder to read and maintain. This inconsistency can cause significant issues when collaborating with other developers, as it reduces code clarity and increases the likelihood of bugs. Overall, paying attention to case sensitivity is crucial to ensure smooth, error-free code execution and maintain the overall health of your code base. Let's talk about the importance of indentation. While it seems trivial, incorrect indentation can lead to confusion and errors. Let's understand why this matters. Imagine you're reading a book where the paragraphs are all jumbled together with no spaces or indentations. It would be incredibly difficult to follow the storyline, right? The same thing happens in coding. If your code isn't properly indented, it becomes hard to read and understand, which can lead to mistakes. Let's look at an example now. In the incorrect code, the lack of indentation makes it harder to follow the structure and flow of the function. While this might still run this code without throwing an error, it is considered bad practice and can lead to misunderstandings and bugs in more complex code. In the correct code, we use indentations to clearly separate the different levels of the code structure. This makes the code more readable and easier to maintain. Proper indentation helps you and others understand the logical flow of your program at a glance. Incorrect indentation can significantly impair the readability and maintainability of your code. Poorly intended code is difficult to follow, increasing the likelihood of errors and misunderstandings. This not only makes debugging and updating the code more challenging, but also complicates collaboration with other developers. Inconsistent indentation can lead to frustration and miscommunication within a team, reducing overall productivity. Moreover, well-intended code is essential for effective code reviews and ensuring that logical structures are easily discernible. Ultimately, adhering to proper indentation practices is crucial for writing clear, professional, and error-free code that is easy to read and maintain. Sixth most common mistake is modifying a list while iterating over it can cause unexpected behavior. Let's explore this. Imagine you're arranging a deck of cards, and as you go through each card, you decide to remove all the red cards. As you pull out a red card, the deck shifts and you accidentally skip over some cards. This constant reshuffling causes you to miss cards, leading to an incomplete job. This is exactly what happens when you modify a list while iterating over it in your code. Let's take up an example now. In the incorrect code, as you iterate over the number of array and remove an element using splice, the array's indices shifts. This causes the loop to skip over elements, leading to incomplete processing. For example, when 2 is removed, 3 shifts to the position of 2, but the loop moves on to the next index, skipping 3 entirely. In the correct code, we use the filter method to create a new array containing only the odd numbers. This approach avoids modifying the original array during iteration, ensuring that all elements are processed correctly. Modifying a list while you are iterating over it, that's a recipe for trouble. This leads to logical errors that can be a nightmare to debug. Your results become unreliable, and maintaining data integrity, especially in applications with large data sets or critical information, becomes a huge challenge. But don't worry, this is a simple fix. Instead of modifying the list directly, use methods like filter to create new lists. This way you keep everything predictable, ensure accurate data processing, and make your code robust and error-free. It's a small change, but a big impact on your code's reliability and readability. Keep coding smart. Let's move to our next common mistake, that is the issue of using mutable default arguments in functions. This subtle mistake can lead to some unexpected results. Imagine you are a teacher and each day you start a new list of students who have completed their homework. However, instead of starting a new list each day, you keep adding to the same list from the previous days. By the end of the week, you have a jumbled list that doesn't reflect who did their homework on any particular day. This confusion is exactly what happens when you use mutable default arguments in your code. Let's look at an example. In the incorrect code, the function addToList uses a mutable default argument list. This means that if no list is provided, the same default list is used across all function calls. Consequently, each call to add to list without an explicit list argument results in adding items to the same shared list, causing unintended data accumulation. In the correct code, we avoid this issue by checking if list is undefined. If it is, we create a new empty list. This ensures that each function call starts with a fresh list, preventing any unintended data sharing and keeping your data organized and accurate. Using mutable default arguments in functions can lead to unintended data sharing, causing multiple function calls to modify the same list. This results in mixed up data, making it difficult to distinguish between different instances of function call. Such issues are challenging to debug because the root cause is hidden in the default behavior of the function. Additionally, this practice can compromise data integrity, especially in applications where the function is called multiple times in varying contexts. By avoiding mutable defaults and ensuring each function call starts with a fresh data structure, you can maintain data organization, prevent confusing bugs, and uphold the reliability of your code. Moving on to your 8th common mistake. Neglecting exception handling can make your code less robust and harder to debug. Imagine you are building a bridge to cross a river, but you forget to account for unpredictable weather or unexpected obstacles without a backup plan. Without a backup plan, your bridge could collapse at the first sign of trouble, leaving travelers stranded and engineers scratching their heads. In our coding world, neglecting exception handling is like constructing that bridge without considering the possibility of storms and fallen trees. The incorrect code simply plows ahead to potential hazards like invalid inputs or division by zero. When faced with these challenges, it crashes spectacularly, leaving users frustrated. Let's look at an example now. In the correct code, the program attempts to divide 10 by the number entered by the user directly after converting it to an integer using parseInt. However, if the user enters something that cannot be converted to a number, like a word or a symbol, it will result in a division by 0 or nan, that is, not a number. This can cause the program to crash or produce unexpected results. In the correct code, we use a try-catch block to handle potential errors gracefully. Inside the try-catch block, we attempt to convert the user input to a number and perform the division. If an error occurs during the process, such as the user inputting a non-numeric value, it will be caught by the catch block. Here we check the type of error using instance of if it's a type error. We log a message asking the user to enter the valid number. If it's a range error indicating an attempt to divide by 0, we log a message stating that division by 0 is not allowed. This way, the program handles errors without crashing and provides helpful feedback to the user. Without proper handling errors, can wreak havoc on your application, causing unpredictable behavior and leaving users frustrated. So, by implementing exception handling, you are not just preventing crashes, you are also improving user experience, enhancing security, and making your code more robust and reliable. Remember, exception handling is like having brakes for your code, essential for the smooth and safe operations. Next, let's dive into the most common and interesting mistakes, forgetting to close files that can lead to memory leaks and other resource issues. Let's imagine you're running a cafe. Each time a customer finishes their drink, they leave their cup on the table instead of clearing it away. Soon all the tables are cluttered with empty cups, making it hard for new customers to find a place to sit. This is exactly what happens when you forget to close files in your code. Open files clutter your system resources, causing performance issues. Let's look at an example now. In the incorrect code, we use fs.readFileSync to read the file synchronously but forget to close it afterward. This can lead to memory leaks and other issues because the file remains open, consuming system resources. In the correct code, we use fs.readFile to read the file asynchronously. This method handles closing the file automatically once the read operation is complete. Asynchronous reading is more efficient and helps manage resources better. Forgetting to close files can cause big problems for your system. When files are left open, they use up memory and other resources which can slow down or even crash your system. If too many files stay open, your system might run out of space to open new ones, leading to errors. This can also cause your programs to run slower and become less responsive. In the worst case, it can lead to data loss or corruption. By always closing files properly, you keep your systems efficient and your programs running smoothly and keep your code clean and your system running smoothly. Hardcoding values is our next common mistake that makes your code inflexible and difficult to update. Let's talk about the dangers of hardcoding values in your code. Imagine you are an artist creating a mural and you mix your paint colors manually each time. Not only is it time consuming, but it also leads to inconsistencies. One day you might get the perfect shade of the blue and the next it's slightly off. This is what happens when you hardcode values in your programming. Let's look at an example now. In the incorrect code, we are hardcoding the value of pi as 3.14. This might seem harmless, but it can lead to inaccuracies because pi is a constant with more precision than just 3.14. Additionally, hard coding makes your code inflexible. If you need to update the value of pi, you have to manually change it everywhere in your code. In the correct code, we use the built-in math.py constant provided in your programming language. This ensures greater accuracy and maintainability. By using predefined constants, we can easily manage and update our code without the risk of introducing errors. Hard coding values in your code can cause many problems. It makes your calculations less accurate and your code harder to update. Every time you need to change a value, you have to find and update it everywhere in your code, which can lead to mistakes. Hard coding also makes your code harder to understand and maintain. By using predefined constants and variables instead, you make your code more accurate, flexible, and easier to manage. Avoid the trap of hard coding and keep your code clean and adaptable. Our last but one mistake is overcomplicating your code, and neglecting comments and documentation can make your code hard to read and maintain. Let's dive into a story to understand why keeping it simple and well documented is so important. Imagine you're assembling a piece of furniture. You have two sets of instructions. One is 10 pages long with complicated steps and no clear labels, while the other is a single page with clear, simple directions and detailed notes. Which one would you prefer? The simpler, well-documented one, right? The same goes for coding. Simpler code is easier to understand and work with, and good comments and documentation act as invaluable guides through the complexities. Let's look at an example now. In the less preferred code, we are using a loop to square each number in the numbers array. This approach involves more lines of code, making it harder to read at a glance. Additionally, there are no comments or documentation to explain the purpose of the code and its functionality, leaving anyone reading it to guess what it does and why. In the correct code, we have simplified the logic by using the map method, a built-in array function. This creates a new array by applying a function to each element of the original array. This one-liner is more concise and readable. We have also added comprehensive comments and documentation explaining what the function does, its parameters, and its return values. This makes the code easier to understand and maintain. Simplicity and clarity are essential in programming. Overcomplicating your code and neglecting comments and documentation can make your code difficult to read, understand, and maintain. Complex undocumented code increases the likelihood of errors and makes debugging a challenging task. Now let's discuss our final common mistake, overusing global variables. While it might seem convenient, relying too heavily on global variables can lead to a tangled web dependency that are hard to manage and debug. Let's dive into why this can be a problem and how to avoid it. Imagine you're planning a travel to multiple countries. Instead of having separate visas for each country, you try to use one global visa for all. At first, it seems like a great idea. Less paperwork and easier to manage. But soon you run into problems. Each country has different entry requirements and the global visa doesn't cover all the specifics. At the airport, you get delayed, your plans get disrupted, and your trip turns into a stressful experience. This is exactly what happens when you overuse global variables in your code. Let's take an example now. In the incorrect code, counter is a global variable accessible by all functions, leading to potential conflicts and unintended side effects if other parts of the program modify it. This can be likened to the shared cluttered workspace where anyone can interfere with your tools, disrupting your workflow. In the correct code, we encapsulate counter within a function that returns an object with increment and reset methods. Each counter is independent, preventing interference and ensuring that changes in one counter do not affect another. This approach keeps your workspace organized and free from unintended alterations, just like having individual desks for everyone. Overusing global variables can create serious problems in your code. When global variables are changed from different parts of the program, it's hard to keep track of what's happening, leading to unpredictable behavior and difficult to find bugs. In large projects, this makes maintaining the code a nightmare. As developers struggle to understand how everything is connected, in team environments, multiple developers might accidentally change the same global variables, causing conflicts and unexpected results. This decreases the productivity and increases the risk of errors. Relying too much on global variables also makes your code less modular, harder to test, and less reusable. By keeping variables within functions or objects, you can make your code more reliable, easier to maintain, and better for teamwork. And there you have it. By avoiding these 12 common coding mistakes, you will write cleaner, more efficient code. Remember, practice makes perfect. Keep coding, keep learning, and happy programming.